The next pitch is from Elisa Hurwitz, presenting Currently.
Thank you very much for the introduction. Recently, NASA conducted a study and identified all-electric aircraft with distributed power systems as the most efficient architecture for future airplanes. However, distributed power systems require tighter power control, and it's necessary to integrate more fast and accurate current sensors. While commercial aircraft mostly need to fly from one place to another, military aircraft need to support several sensors and weapon systems and engage in dogfights and fast maneuvers. Therefore, they need even more agile power systems and faster, more accurate current sensors. A while ago, the Air Force conducted an experiment in which it commissioned low-cost aircraft to be designed. The result were the Predator, or the MQ-1, and the Reaper, the MQ-9. And unfortunately, these UAVs had very high crash rates, resulting in $3.8 billion in damage due to electronic failure. Therefore, the Air Force decided to rethink what parts of the system should be low cost, and thus low-cost attritable aircraft technology was born, in which now there's a trade-off between durability and mass. And low-cost design techniques and materials are still implemented, but the flight-critical systems must still be reliable, and that is particularly true for the power system. We are developing an ultra-fast current sensor to align ourselves and enable these agile power systems and agile power distribution. This should increase reliability and reduce cost for LCAT systems. It's compact and easy to use and scalable, and will also enable more effective circuit protection. We've tested our sensor so far by exposing it to a current pulse with nanosecond rise time. Commercially available sensors misinterpreted the signal or had a really large delay. However, Currently's sensor detected it and tracked it precisely. And this difference in delay of a few microseconds could be the difference between an aircraft maintaining flight or sparking a wildfire. So we were so excited about the results, we decided to look and see how does it compare to other sensors on the market. And the sensors that are designed to detect higher current tend to be more expensive, but they also have a very low bandwidth. Our sensor has higher performance in its current range and in the bandwidth that it can detect, at which it can work. Then next, we looked at the defense market. And typical sensor prices are between $1,000 to $2,000 per unit. But this is dwarfed by the integration cost, which can go up to $1 million per unit to put a sensor simply on a cable or in a particular application. We think that because our sensor is more accurate, that we can provide it at a lower price and a lower integration cost. And the Air Force, if we just upgrade the sensor in 5,000 of its aircraft, then the market is estimated to be around 200 million. However, there are many other opportunities for upgrading sensors in electrical systems in the Air Force. To bring the sensor to market, we're going to team with GE Aviation, one of the top 10 defense contractors, and it commands about 30 to 40% of the electronic systems market share. And they're also recommended by AFRL. And we're also going to team with Caney Aerospace, as they're already involved in LCAT systems, the Agile Prime program, and eVTOL systems. And this sensor also has wide application in the commercial market, in smart grids, in electric vehicles, and in electronic systems as part of appliances. We think that based on our contacts, we can address about 100 million of this market. And to do this, we're working right now actively with SNC Electric as their major smart grid vendor. And they also provide systems for Duke Energy that has also written us a letter of support. And eventually we'll reach out to GE Energy. Initially, we're going to customize our sensor for Air Force applications, as our partners are already active in this area, and this has the lowest barrier to entry. The market's approximately 1 billion. Next, we will migrate to Army applications, as our partners are also active in this area and has a slightly larger market. And then finally, we'll introduce this sensor to commercial applications, as for each military application, there's also commercial application for current sensors. And this has the largest market by far. Initially, we'll customize our sensor for high volume applications in cooperations with the OEM, and we'll mass produce them, leveraging existing manufacturing supply chains, earning a profit per unit sold. But some customers have expressed interest in sub-licensing the technology for specific applications, and we're willing to entertain this idea. So far, we've received 4 strong letters of support from defense and commercial collaborators, 1 letter of support from the Air Force Lifecycle Management Center, which is responsible for upgrading all of the airplanes of the Air Force. And we've also submitted an NSF proposal, and our partners have identified 3 applications for immediate testing. We will use the phase 2 funding to develop a sensor for Air Force applications, test it in an Air Force environment, and validate the sensor in 3 potential applications. And this will ideally position us for phase 3. But to do this, we rely on a team that has experience in electrical engineering, risk management, and strategy. And one of our co-founders, Dr. Farahi, has already successfully brought 14 products to market through startups. And I have spent the last 20 years honing my skills in electrical engineering and materials science and theoretical physics, and have always had the dream of developing and commercializing a technology to help America sustain military superiority and contribute to clean energy. But to do this, we require and ask for phase 2 funding to develop reliable current sensors. And